Hello and welcome to this Simpleware webinar. Thank you for taking your time to join us today. Today's presentation is on CT-based simulation of complex parts and materials in aerospace. Hopefully everyone's joining okay. But firstly, just to quickly introduce myself, my name is Russ Cotton. My role is the Application Engineering Manager for the Simpleware products at Synopsys. My role today will be simply to help coordinate the presentations and the Q&A at the end. Our main presenter today will be my colleague Mike Zilmer and Deepak Patel from the University of Michigan. So I've just got one slide to run you through about the running of today's event. Today's event will be a presentation followed by Q&A. The Q&A will be restricted to a few questions, and we'll finish up the webinar after that. Attendees will be muted throughout, so if your audio is not working or mic's not working, that will be the reason why, but hopefully you can hear us still through the speakers. If you think of any questions throughout the presentation or during the Q&A, please feel free to type those in and submit them as shown on the screen. We'll try and get through as many questions as possible. As I mentioned, we'll just probably go for about 3 or 5, depending on time. But if we can't get to your question, we will follow up by email after the webinar today or later in the week. Just to make you aware, the webinar is being recorded today and will be made available for download. You'll receive an automated follow-up email after the event with a link to download it from the website. If you have any problems throughout the webinar today, just type those into the toolbox, whether it's the audio or screen sharing or anything else. Please get in touch and we'll try and help you out the best we can. In most cases, especially with audio or connectivity issues, it may be best just to rely on the recording as we'll monitor that closely throughout. But with that, I'll hand over to my colleague Mike Zilmer, who will be the first presenter today. He'll introduce himself and also our guest presenter as well.
Yes, as Ross pointed out, my name is Mike Zilmer. I'm the account manager with Simpleware. I'm out in California, and I cover most of the U.S. and Canada. What I'd like to do is give a quick introduction to what Simpleware is prior to handing it over to Deepak. Deepak is going to be presenting some work that he did while he was at the University of Michigan. He's now with Dassault Systems. And so I'm going to be handing it over to him shortly, but I wanted to give you guys a quick introduction to the technology that he used to work on this particular project while he was at the University of Michigan. Simpleware is a company that was a standalone company. It was acquired by Synopsys in 2016, and we're developers of high-end 3D imaging software. And we do have a dedicated sales, support, and services team dedicated to the Simpleware product line. That means that when you call in for technical support, you get somebody who works with Simpleware daily. We do have a global presence, which allows us to be able to work seamlessly with large companies across the globe. And the main areas that we tend to focus on is life sciences, and then materials and manufacturing. Those two items put us in most other industries, but typically speaking, we're working with critical applications where looking at the internal structure of a part or a material is of critical application, and we want to be able to look at it at a deeper level than other tools allow us for. So our product line, keep this very short and simple here, which is that we have our software. We also do human body models, and then we have our services, and those services can range from very run-of-the-mill, just kind of doing one-off projects, to full-blown customized solutions that can automate your processes for you. And so the way our software works is we kind of sit here in the middle. We have image data coming in. Now that image data can be from a variety of sources. It could be a CT, industrial CT, an MRI, micro CT, electron microscope, so on and so forth. We've even received like satellite data. Alternatively, we have customers who have programs that will generate poor quality models and our system can read those in, clean them up for you, and kick out a better quality model on the back end. We have a pretty straightforward offering here. We've got our software plus a few modules to go along with it. Those modules will allow us to output different types of models. Could be being able to generate the STLs. The simpler CAD module allows you to incorporate CAD designs in with your CT data. And then we have our FE module, which is pushing out high quality, watertight simulation models. NURBS is going to give us an IGES or STEP type file. And then on the back end of it here, we're able to output really high quality like STL models for 3D printing purposes, design, simulation, so on and so forth. It is a very open architecture. So down here at the bottom, we've got quite a few scripting languages that are accepted. And so we can really automate and customize this tool as needed as we go. Within, once you bring the data in and you're working on it, we've got all the kind of normal tools within the tool belt to be able to clean up the data and start to analyze the data. Whether it be through a set of measurements or statistical information, or generating, animations, or as we pointed out, the 3D models themselves. In the applications of materials and manufacturing, we focus all the way from the material level, which is what Deepak is going to be sharing with us today, all the way through part inspection, reverse engineering, 3D printing, so on and so forth. So doesn't really matter what we're looking at, as long as we can get a scan to look at it at a level that's appropriate to look at it, then we're able to really read that in and start to work with it. So we read that data in, we take these stacks, and we start to process and create our models. Now what I'm going to do is I'm going to stop there. We could go on for hours about the software. But we want to get you over to Deepak, who is going to share his experience coming into Simpleware, utilizing it as a brand new user on what is a very hard problem. We were very impressed that he chose to tackle this type of problem, and is the reason why we chose to have him on the webinar, and we're very lucky to have him. We appreciate him taking his time. And what I'm going to do, Deepak, is I'm going to change the presenter over to you now.
Sure.
Should be giving you that now.
Can you see my screen now?
Yes, we can.
Okay. Okay, so good morning, everyone. I'm Deepak Patel, located in Santa Clara, California, and thanks, Mike, for the introduction. The work I'm going to talk today is about the title I chose is a city-based simulation for the complex parts and materials in aerospace. And I'm going to talk about a very specific material, very highly complex material, which is very widely used in aerospace and in automotive industries too. And this is a joint work as a part of my PhD work done at University of Michigan with my advisor, Professor Was. And moving forward, few things I'm going to talk today is micro city details of the special material we call as a 3D thick symmetric textile composites. I'm going to talk more about the nomenclature of the material very specifically in next few slides, and talking more about what you can do in a microstructure level, like different kind of studies like porosity analysis, a lot of microstructure imperfections, and bringing those into the Simpleware and how to make a 3D CAD model and a finite element model, including all those details in the microstructure level. And then when you make the finite element model using Simpleware, now you have your analysis tool, which I will talk a little bit about, multi-scale framework, which I use to model the whole coupon levels specimen. And I have some experimental results where I can show the comparison between the simulations and experiments and leave with some conclusions in the future work. So as I said, as a material engineer, you you are interested in a material, very highly complex material, which has a lot of, I call it a material system, which is basically 4 different materials in one system. And as a material engineer, you can zoom into the material and try to understand, characterize the material in a different length scale. For example, in this slide you see, you can go all the way from the quantum scale to all the way from molecular dynamics, micro, meso, macro. So there are different length scales you can be interested in, but for this particular study I have focused on 3 different length scale, and that's why you call it is a multi-scale framework, and including all those microstructure details. So I'm going to talk about the multi-scale also. So this is the slide which gives you a schematic of what particular material system I'm going to talk about. So think about this is a textile composite, 3D textile composites, and the nomenclature is because the thickness direction is relatively high compared to the in-plane dimensions. So we consider it a 3D material, and the reason is, if you see in the left-hand side picture here, think of it as a matrix box, and inside the matrix box a lot of different kinds of fibers, composites, are running through the matrix and leaving a matrix pocket. And the way they run is like there are the carbon fiber, there is a glass fibers, and there is a Kevlar fibers. So carbon and the glass fibers, they run in plane directions, like for example X and Y directions, but the Kevlar fibers, which is basically running through the thickness direction, and which stitch together those in-plane carbon and the glass toes just to prevent the delamination. So the good thing about this particular material, and is very widely used and very popular, is most of the composite community, they face with the delamination problem in a laminated composites, whereas this textile composites, this 3D textile composites, because of the thickness direction reinforcement, the delamination is prevented. Okay, so on the right hand side you see a small a micro city 2D cross-sectional dimensions, where you see all the black fiber toes are carbon, all the white is in the middle at the center, which is glass fibers, and you see those threads which is running in the thickness direction, which is Kevlar, and the epoxy is a SC15 epoxy. It's a high temperature thermoset resin for particular applications. And this is few more details. We studied different architectures, like we call it a thin symmetric, thick symmetric, based on the configurations. For example, on the left hand side you see the carbon on the top and the bottom, glass in the middle, whereas on the right hand side you see it's a unsymmetric structure, right? So the carbon on the top, glass in the middle, with different thickness of the thing. So one of the purpose of the study also was to see how the combination of this material in a stacking sequence influence the material properties, also the thickness or the size effect, how it brings into the picture of the material characterizations. So this is where I use the simple word to do a lot of microcity analysis, because for this particular material they have a lot of details which is needed to be included in the analysis. For example, if you see in the left hand picture on the top, I took a 2-inch by 1-inch specimen, did a microcity study, and tried to characterize a unit cell. And as I said, this is a 3-dimensional, so we call as a in-plane dimensions as a web directions and the warp directions. So you see the symmetricity or the periodicity of the structure, and you try to characterize the unit cell dimensions using those microcity, because there is a repetitive structure happening. And on the right hand side you measure all the individual fiber toes cross-sectional dimensions. So those inputs can be used to construct a finite element or the CAD model. And below figure you see we did some SEM studies, scanning electron microscope, to characterize the fiber volume fraction for individual fiber toe for carbon, glass, and Kevlar. So the particular machine I used for this particular material system is a SkyScan 1173 microcity system. There is already a iterations of study, like which microcity scanning system you should be using depending upon what specimen size you are using and what kind of resolution you are looking for, right? So this particular system I choose because of the reasons you can see in the slide, because it has a large sample chamber, and I could scan as a 17 micron, and the specimen size was 2 inch by 1 inch, and the thickness was 0.6 inch. And you see here, like if you try to resolution more or less, like it all depends on the scanning time, and also the most challenge in this problem was there's a 4 different material system, which is kind of a carbon, glass, Kevlar, and epoxy, whereas the Kevlar and the epoxy has a very close density. So because of the density, when you get the CT images, the scanning images, you have when the material has a density difference in a very close margin, you have kind of a the grayscale is kind of a challenging problem for you to differentiate between 2 different material systems. So we had to try with a different kind of micro-city scan machines to come up with the good resolutions we can use in our model or analysis. So this is another flow chart where you can see in a very schematic way that after you do all the scanning in the left-hand side and you get the images, you get all the 2D cross-sectional images, and then you reconstruct them and make a 3D model of the whole of the specimen, right? And when you make those images, bring it to the simpleware and reconstruct the 3D model inside the simpleware, and you can individually segment all the fibers, like all carbon, glass, Kevlar, and epoxy individually. So that's the beautiful of this simpleware, that you can clearly differentiate between different material system based on the grayscale difference and the density difference from the images. And when you get the finite element model, you can bring it to, I use Abacus for my analysis, so you can bring it to any finite element software as an input file. You can export from the simpleware. And this is a schematic of the top figure is when you have no imperfections. So as you see here in the bottom picture, like when you see the micro-city images, there's a lot of fibrous undulations and imperfections already inbuilt into the structure, which need to be included in your simulations, which is very difficult to manually capture if you try to simplify your model. For example, in the top you see all the fiber stores, I'm assuming is straight, and everything is perfect. But in the bottom figure, you see how beautifully all those undulations or the imperfections has been captured in simpleware. So this is a unit cell analysis where you see we are pulling in the web direction. So also this material is the properties are very directional dependent because of the reinforcement is only in one directions. So obviously the properties are different in the web direction and the web direction. So this is, I'm showing you the tensile loading in the web directions. As you see here, all the metrics in the bottom figure, all the fibers are fiber 2 are breaking in the pulling directions, and the transverse fibers are having a lot of matrix cracks, and even in the Kevlar fibers, and there is a lot of matrix cracking happening in the epoxy, as you see on the left hand side. So this is, but we step up into one more scale, and we decided to go to do for the whole coupon level. So we did already the unit cell analysis, but we did for the whole dog bone specimen, as you see here. And to characterize the whole dog bone and to simulate, we use 3 different length scale, which is included in my PhD thesis. And as you see here, the bottom figure, the whole specimen dog bone coupon is a macro scale, I call it, and you saw is a A and B. Whereas you see in the grip area, where I'm holding in the lab, I'm calling as a part A, which I'm kind of homogenizing to reduce the computational model, right? But the part B, where I expect the specimen to be failed, I scan the whole coupon, but individually segmented individual fibers in that the region B. Okay, and in the region B, if you zoom in, there are a lot of at least 9 to 10 RVEs or unit cells in the part B is included, which is kind of a major scale I'm talking about. And inside every fiber toe, we have a micro scale in a computationally, which is I have worked on my PhD, and we call as an NCIL model, where you can characterize individual fiber to all the elastic properties plus damage plus failure using the smeared crack approach and using the NCIL method individually each of the fiber toe. So basically it's a 3 different length scale, which is kind of very hard to explain in a few minutes, but I have already published this paper, so always you can go back and refer to the paper for more details about the length scale. So here, as I said, more details, the part A is homogenized because I'm trying to reduce the model size, and we know that the most of the failure will be happening near to the curvature area where there is a change in the cross-sectional area between part A and part B. So those parts has to be my focus where I'm individually segmenting those fibers. Okay, and this is how you characterize the homogenized properties, because you take a unit cell and use a periodic boundary conditions and get all the properties from E11 to G23, like a orthotropic properties, and you assign those properties to the part A. And then this is a comparison between when I took from a unit cell level to the dog bone coupon level, and when you choose a different length scale, different specimen size, obviously I'm choosing different SkyScan machine. For example, for 2 inch by 1 inch, I'm using the SkyScan 1173 because of the certain features they have. And when I'm going for a longer specimen, like a half coupon or the full coupon was kind of a 6-inch long and 0.6 inch thickness. So I'm just using the SkyScan 1076, and you can see all the details, all the specification of individual microcity system. So to reduce the model size, I use the half coupon model, and because of the symmetricity, I try to copy and make the full coupon model using those images data. Okay, in simpleware itself. So now when you do the modeling and the finite element mesh, everything is done in simpleware, and this is how it looks like. In the top left figure, you see the whole coupon has been modeled with epoxy, and if you zoom in, how beautifully those geometry, the curvature of the corners has been captured using those images and individually modeling the fiber toes. The right hand side is a finite element mesh picture of the whole coupon. Okay, so I have used quadratic tetrahedral element for these simulations, and in the bottom figure you see that 1:1 comparison between the whole dog bone coupon, which I used for the experiments for tensile loading, and on the right hand side you see the full scale model, 1:1 scale model, which is being imported and be ready for analysis. So now when I use this multi-scale approach and try to run the model in the analysis using the model I got from simpleware, this is the comparison between the experiments and the simulations. So as you see on the left hand side, the experiments are failing near to the gaze area, which we expected. And also the challenge here is am I able to capture the stiffness, the strength, and also the failure mechanisms? Because if I'm able to capture, then I can have a validation of my damage model, or what the model I worked on, the NSIL model. So you see the beautiful comparison where you expected in the simulations also, a lot of fiber toes in the pulling directions are getting actually fiber toe breakage. Okay, and you see the right hand side top picture, that where there is a comparison between the experimental curve, between the black curve and the red curve, which is a very good correlation between the experiments and the simulations. This is in more details about like for different images of fiber failure, the matrix failure, and in the back side and the front side of the specimen, and kind of a correlation with the experiments. Okay, so this, in summary, we could develop a reliable, very multi-scale analysis tool, which we call as a NSIL model, and which is in my PhD work. And anybody, I have given some references at the bottom, which is already published in Composites Part B, this particular work. And anybody is interested, please reach out to me, and I'll be able to give some more details. And so we had a multi-scale model, which is NSIL plus near crack, but the CAD model is totally brought from the simpleware, which is purely microcity based. And the advantage of this, the whole work was to demonstrate that how the image based model, which includes every imperfections, all the porosity, all the curvature, all the imperfections inbuilt in the fiber tools, all the waviness, which is included in the analysis. So there is no assumptions in this analysis, and this is for the whole coupon. So there is no universal analysis, right? So, and also we have done the RV level and also the coupon level and also the experiment. So there is a very good correlations with all of them, as you see. And these are the references, and I think I'm ready to take some questions here.
Great, thank you, Deepak. I'm just handing the controls back to Mike, who will conclude the presentations today.
Sure.
There we go. Yeah, thank you so much, Deepak. That was great. Yeah, just up on our screen right now, I have some follow-up information. But before I really get into that, I guess I'll kind of walk through this real quick, and then we'll open it up for Q&A. We do readily offer a 30-day free trial. Just need to go to our website and submit a request, and we'll get you up and running there. We can do a personal demo of the software. We've got plenty of resources online, some great 15-minute webcasts, and longer, more extensively detailed webinars. Again, my name's Mike Zillmer. My email address here is at the bottom. You can contact me, and I can get you in contact with Deepak if need be as well. And then here's our website at the bottom. So we really want to go ahead and open it up to the audience here for any questions that may come up about Deepak's presentation.
Great, thanks, Mike. I'm just waiting for the questions to come in, and just to remind everyone that we'll be sending out emails afterwards today with a recording to download. The recording today. Yeah, Deepak, just one question that may be coming through. When you segmented the individual fibers, did you model contact, or how did you deal with the interactions between the fibers and different properties?
Right. So the question is, how do I interact individual fiber segmentations and the properties, right? So as I say here, as I mentioned here, I have the micro scale. We have a 3 different length scale. So when you have a fiber properties and the matrix properties in a micro scale level, so you can already homogenize using our method called NSEAL, where you get the homogenized properties for the fiber toes, which you can assign to the fiber toes you model in simple way. So that's in the mesoscale level, you are homogenizing the fiber toe, which from the CT images, but the properties has been extracted using the microscale NSEAL. And as I say, the interaction between the fiber and the matrix, we have used the abacus contact definitions to make sure that the bonding between the epoxy and the fibers.
Okay, great. I think that's maybe answered 1 or 2 questions that have come in. Maybe a kind of follow on that. It says, based on the figures you showed, it appeared that you segmented the toes from the matrix and not the individual fibers from the matrix. Is this correct? How difficult was it to segment the toes in the matrix for the textile coupon you worked with?
Right, so that's a very good question. So the work was pretty challenging, and that's the reason you need to take a wise decision, like when you are individually segmenting the fibers and the matrix separately, discretely. The work becomes easy when you have a very good resolution images. For example, what material system, this particular material system, I had a difficulty of kind of epoxy, the matrix and the Kevlar fiber, and they are very close density. And when you do the CT images, because of the density difference of your materials, it's hard to get the contrast, the grayscale differences in those individual materials. So there you have certain challenges, and it all depends upon the resolution and the good quality images you get from your micro CT systems. But the software point of view is very robust to segment out when you have those grayscale differences in the tool.
Great, thank you. Yeah, I think you touched upon another kind of question that's come up there about what made you choose Simpleware for this challenge in processing this 3D imaging data.
That's a very good question. So when I was in my PhD program, I was trying to I was looking for some solutions to how to handle this kind of, especially in these textile composites, a lot of imperfections are inbuilt, and how to capture those details in the model, and including everything. So I evaluated a few other softwares, and I had a trial license for the Simpleware. I was in contact with Karim Jeng, and then kind of we evaluated, and it served the purpose of what we are looking for. It's very robust, and you can easily, like the manual segmentations, yes, you have to do the manual segmentation that time, but the thing is, if it has a good quality image, the tool was very handy. So we choose a Simpleware to go ahead with this this project.
Okay, that's great. Thank you for explaining that. In terms of the models, how large was the model in terms of numbers of elements, and what was the name of the code you used for the simulation?
Right. So if you see here, this is the whole dog bone coupon, right? So and I use the tetrahedral element. So the total number of elements, if I remember correctly, was around 500,000 elements. And the computation time, the good thing is the code I used is written by me and my professor. It is a part of my PhD work. It's called NCIL. It's a concentric cylindrical model. We call it a two-seal for the two cylinders, and we call it a NCIL because of the NCIL code. So the publications I have that will give you more details about the code, and that code actually can characterize can bridge together between the micro scale and the homogenized toe scale. And yeah, that's how. And the good thing about is, because even if you have a huge model, because our code was mostly analytical method based because of the multi-scale, because that's a good big question, because I want to emphasize here that the computational tool is very efficient in terms of, because of the micro scale is based on analytical solutions. So that's the good thing about our code.
Great, thank you. And I guess people can look at your publications for more information on that process and the simulation.
Sure.
Great. I think we'll probably start to conclude the Q&A there, as we've just run over the half hour mark. In terms of how you use the Simpleware, could you just kind of maybe just walk us through from how you use the software? So I guess you started from importing the stacks of images. Could you just kind of walk us through the steps in the software quickly, and then when you kind of finish with the software, and what kind of files you imported and exported, perhaps?
Sure. So in brief, as I said, I think I had one slide just explaining the workflow. So the workflow is you have your specimen, and depending upon what kind of specimen you want to analyze, and you need to choose a particular micro CT system or different kind of imaging system, where you get the X-ray or you get all the micro CT images, and you have all the 2D images in your hard disk, right? You got all the images from the X-ray, and then you bring all the images, all the 2D images to the Simpleware, where you can import all the images. And then Simpleware has all the inbuilt functionality where on the tools available, that where you can I will say you can segment it. You can reconstruct 3D model from the 2D images by stacking together in all X, Y, and Z directions. So it's a fully 3D reconstructed model, and while doing the reconstruction, you can individually, discretely segment different material, different fibers based on the grayscale differences, which is a lot of efficient tools are available where you can differentiate those grayscale in the images itself, and you can model a 3D CAD model of the things. And when you made the 3D CAD, then you can mesh it inside the tool, right? And they have different kind of finite elements. All the commercial finite elements are available inside the Simpleware. Once you mesh the thing, you can export to Abacus as an input file, .inp file, right? Which is basically is you need for to move ahead with the analysis in Abacus. But also they have interface to export in a different file formats for different other softwares too. So that's pretty much the workflow. When you get the input file, everything is there, all the finite element information, all the material information, and then you're good to run in your simulations in Abacus.
Great. Thank you very much for taking your time to answer that question and all the others that have come in today. Just in terms of the questions, we will, I know we haven't got through all of those, but thank you for contributing those questions. We will get back in touch with you by email as soon as possible after the event throughout the rest of this week, hopefully. So sorry if we couldn't get to your one particularly, but we will try to get back to you by email afterwards. Thank you to Mike and Deepak today for presenting. I'll just hand it over back to Mike quickly for any final remarks and conclusions.
Thanks, Ross. Yeah, no, thank you, Deepak. We really appreciate you taking the time to do this for us. Your application, as I mentioned in the beginning, was one that we felt was a complex application that others may not even necessarily try to attempt. So we'd like to show people out there that these kinds of applications are very doable. To one of the points you made earlier, or to one of the questions earlier, which was, why did you choose Simpleware for this particular project? And I think it's relevant for us to say that when it comes to building simulation models from CT or MRI or that type of data, Simpleware is considered the best in the business when it comes to doing that. We have an excellent methodology to generate watertight simulation models that they just work. And the last comment I'll make is that I was very proud of our services team, our support team, because they helped Deepak, right? And I remember him saying that in the beginning, the meshing or the segmentation was kind of rough, but once he kind of sat down with some of our support guys, kind of learned some of the tricks of the trade within the software, he said it really started going much faster and much easier, and life got much better for him.
That's right.
So, go ahead. Yeah, go ahead, please.
Yeah, so thanks, Mike. Yeah, so I had a fully the tech support, and while I was picking up the software and trying to learn it and then trying to implement in my work, so I got a very good support from your team. So thanks for that. Yeah, and then if you have any questions, the listeners, please reach out to Mike and me. My email ID is on the slide, or even and if you need any details about the methodology or any kind of details about these presentations, please reach out to me and Mike. So thank you so much.
Excellent. Well, thank you again, Deepak. Thank you, Ross, for your help. And I believe that concludes our webinar for the day.
Great. Thanks, Mike. Thanks, Deepak. Thanks all for listening. Thanks. Bye.
Bye-bye.
Bye.